Okay, it's time to start again. Our next speaker is Vercruysse, who's going to speak on a lax-monoidal setting described by Hom-Hopf algebras. Thank you.
Hello, thank you very much. I hope you can hear me. First of all, I would like to thank the organizers to organize this event in this hybrid format so that I can follow it. Although I truly hope that next time I can be on site, because following some lectures, sometimes with yelling kids in the background, it's not ideal. But well, for the moment, it works like this. So I will indeed talk about by Hom-Hopf algebras and a Lexmonoidal set to describe these objects. And I should say this is a joint work with Gabriella Böhm. And as many of you might know, Gabi recently has left academics and stopped doing research shortly after we finished the paper. I hope there is not a connection between the two events. But when I asked Gabi if it was okay that I talked about our joint work on this conference, she said that it was fine, but I should not dedicate my talk to her memory. So that is what I will now officially do. This talk is not dedicated to the memory of Gabi Böhm. Okay, so I will start by explaining you what is a Hom algebra. So a Hom algebra is a vector space. Well, you can do it in general over commutative rings or even in monoidal categories, but to keep things as simple as possible here, I just consider a field and vector space is over a field, okay? So a Hom algebra is then a vector space endowed with 3 linear maps. So 2 of these linear maps are the same as what you have for usual algebras. You have a unit map and you have a multiplication map. But then there is a third map, which is an endomorphism of this vector space, and such that we have the following axioms to hold. So there is a sort of associativity and unitality law, but these associativity and unitality are a bit deformed with respect to usual associativity. So you use this endomorphism in order to express this associativity. So alpha of A times a product BC should be the same as the product AB times alpha of C. And in the same way for the unit, A times 1 is alpha of A is equal to 1 times A. Okay, no, like this. Okay, so in the same way or analogously, you can also define what are Hom-Lie algebras. In fact, these Hom-Lie algebras came first, and then only the associative Hom algebras. There are Hom-Co algebras, Hom-B algebras, Hom-Hopf algebras, and so on. And more recently, even more general things appeared, these B-Hom algebras, where you now not have just one linear endomorphism, but you have 2 endomorphisms, alpha and beta, which are commuting. And now the associativity and unitality constraints both involve the alpha and the beta. Okay, and in the same way, again, you have B-Hom-Lie algebras and co-algebras and bi-algebras and so on. Okay, so depending on the properties you have on these endomorphisms, alpha and beta, you can mainly distinguish 3 cases. So the theory of Hom algebras can be developed at different levels of generality, let's say. So first option is to take these alpha and beta just any kind of linear maps. In that case, the theory is quite weak, but let me first tell you the other option. So you can just have alpha and beta the linear maps, or they can be, let me call them homomorphisms, by which I mean that they preserve the operations you have. So they have to preserve the multiplication and the unit in the associative version that I showed you. Or the third option, which is the strongest assumption, is there you assume not only that these endomorphisms preserve the operations, but also that they are invertible. So they are really isomorphisms. Like I already said, so in this linear case, there the theory is rather weak. There is not many interesting results that can be obtained, just because these alphas make that the usual theory cannot be extended to this setting. The other extreme is to ask that these alphas are isomorphisms and preserve all the operations. In that case, you can basically do everything, by which I mean that many classical results can be developed in this Hom setting. You just have to plug in the alphas, the endomorphisms at the correct places, but you can basically follow the classical proofs in order to obtain results here. And then there is this intermediate setting where you have endomorphisms that preserve the operations, but are not necessarily invertible. And in fact, the theory was motivated by examples of that kind coming from physics. I put a question mark here because I don't know anything about the physics that is behind it, but apparently they came from physics. And in this setting, still quite some results can be obtained, but the proofs really change in that case. And some results cannot be obtained, seem to be out of reach, at least for the moment. So what I want to explain you now is, or what I want to answer are the following two questions. Firstly, why is everything working so smoothly in the isomorphism case? And secondly, why does it not work as smoothly in this homomorphism case? So the answer to the first question is already something that is known. That is a construction from Stef Kanepeel, who I think is in the room, and Isar Gooivaerts, one of his PhD students. About 10 years ago, they showed that they defined this Hom construction on any monoidal category. So suppose that we start with a monoidal category C. Let's say it's a strict monoidal category. And then we can construct a new category, which I denote CG of C. And it works as follows. So the objects in this new category are pairs A alpha, where A is an object in the underlying category, and alpha is an isomorphism in C, so an invertible morphism in your category. And then a morphism in the new category is just a morphism in the underlying category, which is compatible with these endomorphisms. Okay. Well, I started with a monoidal category, C. So this new category that you construct, it's again monoidal. The monoidal product is quite easy. You just take the monoidal product on objects and morphisms in the underlying one. The monoidal unit is the monoidal unit of the underlying category with the identity map. And then the interesting part is that you can endow this category with non-trivial associativity and unitality constraints. Namely, you can use the alpha and the gamma of the third object in here to define this associativity constraint. And you use also the endomorphisms to define the unit constraints in this monoidal category. So this turns out to be a true monoidal category. And so when you have a monoidal category, you can compute what are the algebras in here. And then, oh no, I forgot to say this here. When your underlying category C has a braiding or symmetry, then this survives for this new category CG, right? So when the initial category was braided or symmetric, then the new one is also braided or symmetric, and you can basically use the same symmetry. So the nice thing now is that you can compute what are the algebras in this new category. Let's see what this gives. So if you take an algebra in this new category, first of all, it has to be an object in your category. So it is an object in the underlying category together with an isomorphism. Then it needs to have a multiplication. So when you ask for a multiplication to exist in your new category, you need a multiplication map in your initial category, but the compatibility with alpha says that alpha will have to be multiplicative. So it has to preserve this multiplication. Okay, then for an algebra, we need a unit. So the unit needs to be a morphism in your new category, which means it's a unit in the underlying category. And again, it has to be compatible with alpha. And this means now that your alpha preserves this unit. So what we end up with are objects with a multiplication and a unit, and an isomorphism alpha that preserves this multiplication and unit, so that you can think of as an algebra isomorphism. Now, if you look what associativity means in this new category, because of the non-trivial associator you have in your category, the associativity constraints becomes exactly the associativity constraint of a Hom algebra. So the only difference with what I wrote before is that now there is this alpha -1, which is used instead of the alpha at the other side. But since alpha is bijective, is invertible, you really have the same equality as before. Also, if you look to the unit condition, you get exactly the unit condition for the Hom-Hopf algebra, for the Hom algebras. So you can conclude that the algebras in this new category are exactly the associative Hom algebras, where this alpha, where this endomorphism is really an automorphism and even an algebra automorphism. Okay, these Hom algebras now are often called monoidal Hom algebras, which is a terminology that Stef and Isar gave to it. And as I said before, the theory works very well in that setting. You can do the same thing for Hom-Co algebras, Hom-Lie algebras, Hom-Hopf algebras, or the bi-Hom cases if you adapt your category a little bit. And so all the results that indeed go true for these, let's say, monoidal Hom algebras, where the alphas are isomorphisms preserving the structure, it follows from the fact that, well, you are working simply in a certain monoidal category, and you can develop, as everybody knows here, I guess, a lot of theory just in general monoidal categories. So it's just an application of a theory of algebras, co-algebras, Hopf algebras, and so on in monoidal categories. Now, the question that remains is whether a similar approach could be possible in case where this alpha is not invertible. So can we also develop a monoidal setting such that the algebras, co-algebras, and so on in this monoidal setting are exactly these Hom algebras and Hom co-algebras for which alpha is not invertible? In order to answer this question, let us look again at this associativity constraint in the category constructed by Kanapel and Gooivaerts. So this associativity constraint used, as I explained before, they use the endomorphism, but also an inverse of the endomorphism for another object. Right? So if you want these endomorphisms not to be invertible, you do no longer have a map like this. Right? But what we can do is we can use gamma instead of gamma minus 1, and then we have two maps. In fact, so if you take a triple tensor product, you can use the alpha on the first tensorand to have one part of the associativity constraint, and you can use the gamma on the other side of the triple tensor product to have another associativity constraint. So what you see here, instead of having one single map going from one bracketing to another bracketing, you have two different maps pointing to the same object. Well, this is exactly what happens in lax-monoidal and oplax-monoidal settings. So let me take a short break to explain you what are lax-monoidal categories. So they are, I guess, a bit less known than monoidal categories. That's why I would like to recall what is the definition. So in a lax-monoidal category, different than in a usual monoidal category, you do not just have a bifold tensor product and have all higher tensor products following out of that using your associativity constraint. You suppose from the start that there are n-ary operations for any n. So you have an n-fold tensor product for any natural number n. And then you need suitable associativity and unitary constraint conditions, which basically say that in the lax monoidal setting, that you can add brackets in any order you want, and you will obtain the same result. Right? Oplax is more or less the same thing, only the arrows go in the other direction. So here you can remove brackets in any order you want, and you will always get the same result. Okay. So in the lax-monoidal setting, these arrows that you have from add or remove brackets, they are not necessarily invertible, right? If these arrows are isomorphisms, then you have usual, let's say, strong monoidal categories, the usual monoidal categories. If they're only half of the arrows, to say it loosely, are invertible, then you would have skew monoidal categories. So these lax monoidal categories at once generalize skew and usual monoidal categories. Okay, now why are these lax monoidal categories interested? Well, for that, I want to make reference to what is known as the microcosm principle. So to define in category T an object with a certain structure, the idea is that you need a category which has a categorified version of this structure. So if you want to define what is an algebra, which is an object with a multiplication, then you need a category with a multiplication. So usually we think of this as a monoidal category. But now a bit strange, if you want to define what is a co-algebra, you need a category which is still monoidal. You still need a monoidal category, right? And for a bi-algebra, you need two monoidal structures. The bi-algebra, you have an algebra structure, a co-algebra structure, which are compatible. So then you need two monoidal structures which are compatible. So you need what is called a duoidal category, or a more particular case of it, a braided monoidal category. Now, using lax monoidal structures, you can more or less improve this. So here, as I said, it's a bit strange that you have two dual notions on the algebra side. You have algebras and co-algebras, but on the category theory side, you have just one. For both, you need monoidal categories. So you can restore the symmetry by taking the lax picture, and then you need oplax monoidal categories to define what are algebras, and you need lax monoidal categories to define what are co-algebras. And in order to define what are bi-algebras or Hopf algebras, you should combine an lax and an oplax monoidal structure in a duoidal way, We could not find a reference for such a structure, but it's something which is clearly possible. You can consider categories which has at once a lax and an oplax monoidal structure, which are compatible in a suitable way, such that you can define algebras and Hopf algebras in such a setting. Okay, let's go back to the Hom-algebras and what we wanted to say about them. So I will construct now a variation of the category of Canapel and Gooivaerts, which will become oplax monoidal, right? That's the idea. So the objects are the very same as before. You have pairs in the underlying category and endomorphisms. The only difference now is that I do not suppose that the endomorphisms are invertible, right? Because that's exactly what I want to describe. I want these Hom-algebras with non-invertible endomorphisms. So I take the alphas to be just endomorphisms, not isomorphisms. And the morphisms in the category are the same as in the Canapel-Janssen case. So they are just morphisms in the underlying category compatible with these endomorphisms. Okay, now using this diagram that I showed you before, you have these two associativity constraints, let's say, one for where you put an alpha on the left, which removes one type of brackets, and one where you put an endomorphism on the right to remove other type of brackets. Using these maps, you can really build an oplax monoidal structure on your category. So this is similar to what was explained in one of the previous talks. You have, in principle, oplax monoidal structure have an infinite number of information. You have infinite tensor products and infinite many compatibility constraints. Well, if you have just this information, you can build all the rest from this information. It involves some work, but you can really find out a complete oplax monoidal structure just using this diagram. And then what happens if you look what are algebras in such a category, you get Hom-algebras. Well, not entirely, because now I have been ignoring the unitality part. So what we truly have, if you work with what I explained you so far, is that you can consider non-unital Hom-algebras in this oplax monoidal setting. So I didn't say anything about the unitary part of this Lexmonoidal structure. So it's just an oplax monoidal structure without unitary conditions. And so in correspondence with the microcosm principle, you have a monoidal category with a oplax monoidal structure without unitary conditions. Well, you can describe with that algebras without units. So the non-unital Hom-algebras are exactly the non-unital algebras in this oplax monoidal category that you construct this way. Now, what about the units? Well, if we want to add the units, something happens that we did not really expect it from the beginning. So let me try to explain what is a strange phenomenon that happens if you want to also describe the units for the Hom-algebras. So I go back again to this Hom-associativity. So the Hom-associativity was alpha of A times BC should be AB times alpha of C. And for this, we needed an associativity constraint in our new monoidal category of the following form. So you have a triple tensor product, you send it in one way to applying an alpha on the left, and the other direction you send it to applying an alpha on the other right tensorant. Now for the monoidal unit, the Hom unitality tells me that A times 1 is alpha of A equals 1 times A. So for this, I need a unitarity constraint of the following form. I have a 1 tensor A, and I need to send it to alpha of A, and the same A tensor 1 need to be sent to alpha of A. So you see that the arrows go in the other direction. So the strange phenomenon that we have is that the associativity behaves in an oplax monoidal way, whereas the unit, they behave in a lax monoidal way. And so the way you have to do it correctly, or what follows from it, is that we need a certain monoidal structure which behaves where we have n-fold tensor products, right? Which behave oplax for all positive n, and they behave lax for 0. Right? So the 0-fold tensor product is just a functor from the one object category to C. So it gives you the monoidal unit in your category. Right? So now it looks a bit strange. You have some part that is oplax, some part that is lax, and everything has to work coherent. Well, it turns out that you can do it. It becomes quite technical. It requires some combinatorics to write all the coherence conditions. I refer to the paper for more details, but the main message is that it can be done and it works. And so what are the conclusions? Well, we can indeed describe Hom-algebras with non-invertible endomorphisms as algebras in a certain monoidal setting. And for that, you need a lax monoidal setting, which is oplax for the positive part and lax for the zero, for the nullary part. Okay. In the same way, you can describe what are Hom coalgebras. They are exactly coalgebras in a suitably constructed Lexmonoidal category, which is lax in the sense that the positive part now is lax and the zero part, the nullary part, is oplax. Then if you want to describe what are Hom bialgebras or Hom-Hopf algebras, you have to combine both kinds, right? So you will have a category which has two Lexmonoidal structures. For the first one, it is lax for the positive part and oplax for the zero part. And for the next structure, for the second structure, it's lax for the zero part and oplax for the positive part. And then everything has to be compatible in a, let's say, duoidal style. In the same way, you can adapt everything to also cover the bi-Hom versions. So where you had two different endomorphisms that commute. And yeah, for more details, I just refer to the paper, which has appeared in Contemporary Mathematics. It's a proceedings of a conference a couple of years ago in Nanjing, or you can also find the paper on arXiv. Okay, that was all.
Thank you very much. Do we have questions?
Okay, hello, Joost. I have two remarks. The first remark is about the terminology. So in the paper of 2011, we called these Hom algebras monoidal Hom algebras. And you said that the terminology was due to myself and Isaac Goivaerts, which is not the case. It was the referee of the paper that insisted on this terminology. And the second one is maybe also interesting, and a question maybe I don't think you have something similar here. So, but in this monoidal situation, we had this monoidal category, which had where the associativity and unit constraint were not strict. So, which made it promising because it is always nice to have such a thing, but there it was also shown that this category is equivalent to one that is a strict one if the underlying monoidal category was strict. Now, my question is probably you don't have such a thing here.
No. Well, now I'm not sure if I answer your question. So no, it's not strict here. No, you cannot strictify. But I thought you wanted to say something about that. It follows from your results that you can really see a Hom algebra just as usual algebra with an isomorphism, right? And your category of Hom algebra, the category of Hom algebras is just equivalent to a category of usual algebras with algebra isomorphisms. Something like this, indeed, we don't have. So it's not that in this setting, you can indeed just say, well, any Hom algebra is just a usual associative algebra together with an endomorphism, which is no longer bijective. So this is not true. And I think this is related to what you said, that you can completely strictify the thing.
And it's good that you don't have that.
Yes, it's good that you, so like I said, the aim of this work was to show that indeed this Hom setting with non-invertible endomorphisms, it's really different from the classical theory, and it's really not following completely from the classical. So indeed, it's good that we don't have a result like that. It really shows that a Hom setting with non-invertible is, you are doing new things that are not known, that not follow immediately from the classical theory.
Okay, thank you.
More questions? If not, let's thank the speaker again.